try, as I said, quizzes are important, so.
Yeah, I looked through it, but
Yes, okay. Okay. So we have a homework. One due on 24th. Have you guys looked into the homework? It's overwhelming for sure because it goes, it goes a lot, but then I asked for only two. Only two is to be submitted.
on the way.
Only two questions are to be submitted. You did notice that, right? Otherwise, you just would give up. You say that, no, I don't want to take the class and leave.
I forgot, almost forgot that. We had to submit only two.
Only
I was
two.
taking like 28.
No. 28 questions, that would be unreasonable, I think. I think very unreasonable. Yeah. So, no, only two questions. Read the first part of the, before you look into the last part. Look into the first paragraph. It's only two questions to be submitted. Okay. It's mostly a review. The expectation is, I don't think anyone is fluent. Most of you are not fluent in whatever is written there. But the expectation is that at least you know what to do. Okay. So you, it's like saying that if you think of a 200 level physics class and you give them a lot of examples with algebra, and you know that they are not fluent, half of the class is not fluent with algebra, but you still give them, oh, this is what is expected. So here we will redo these things so many times that you will get used to that, but this is what it is about. We will manipulate these kind of equations. So does that help? Did I justify that? Sufficiently? Yeah. Okay.
Is it moving? I don't know.
It's not moving because probably I gave this. How do we do this? Because if I turn it, then you won't be able to get it here, right?
No, I set for this one and the
No?
second one for this one, but it's not moving anywhere.
Yeah, it's not moving.
Is on.
It seems to be on.
It's on.
And I did remove the battery. Okay.
Sometimes if you're just moving around a little bit. You might say that.
Or hit it.
Huh?
Or yeah, or
Hit it.
Is it?
It won't.
I do that.
Engineers doing that. It's not okay. So physicists doing is okay. Well, I don't know.
Maybe
No, the camera is broken.
the TV remote to leave.
I
Did you
don't
change
think
it
so.
back?
I was, I think, careful of that.
Yeah.
I tried not to mix it up. Oh, what else can go wrong? Yeah, so
It was moving a minute ago.
a minute ago it
Yes.
was moving. I see. Is it locked?
Seems loose.
Yeah, it was loose, but yeah, so that's how.
It is supposed to be like blue light.
Yes.
Yeah, blue light is, that means the power is on.
It up like that.
Other again?
Can you turn it like jack in the website?
Uh-huh.
It leads up.
Oh, that up? No.
No, the jack in the website.
Can you know? Like if you take away the power. And then it comes back with the power. Oops. You have to.
Oh, it's moving right now. I was resetting them.
What do you think happened?
Or maybe all the commands are delayed. And now they're all hitting now.
Make it a little horizontal. It seems to be little. Oh, why is this not locked? How do you lock this? Okay. Seems horizontal. There's supposed to be a, what is that called, level? I cannot see it. Somewhere there is level. Yeah. Okay, let it be like this. I think we can manage.
It's okay. Can you turn it the other way? More.
This
I
way.
wanna make sure that it shows
Because I was
this one.
thinking if I put the corner here. I can get this one and that one, it's just that I have to circle the whole world around. Do you think that's better or, because if I turn it this way, you won't be able to get it, right?
No, just a little bit more. Yes, that's,
This way?
yeah, that's good.
Okay,
I think I can,
then how will you get that board?
it will turn the camera.
Okay, I'll let you do it.
Oh, it's okay with this one.
You can turn that around to you, I think. I don't know.
Not showing anything.
Go to video, yeah. No, good, yeah, now it's, yeah, okay.
It's not moving.
Still not?
Mm.
I thought we got. Oh, but it only moved there, they're not using the remote, right?
Yeah, maybe you want to control that.
I think it reset.
I do. Let's try the battery, how about that? There's a small chance that I switched the battery. Ah, I know what could have happened. Hold on, hold on. Yeah. Okay. I think the point is this represents the camera. The
Mm.
top, there are two 1, 2, 3s.
Oh, I have
One
to
on
use
the
that.
first row and then on the second row. This stands for the camera. It can handle 3 different cameras.
Mhm.
So
Mhm.
first you have to press 1 to activate that
This
camera.
one.
So somehow in between all this yesterday and today,
Okay.
we press the camera. Yeah, so okay. That works. Okay, so now I can change the battery first.
Now we know.
Yeah, I think, yeah,
That's right.
maybe make this split it, so not that. Better?
Yeah, it looks.
Yeah, better. Okay, you want it like this, right?
Yes.
Hopefully, this will. This TV also will get, okay, a week or something. Then I know, I think it was Abdullah, you who used to really like to see the TV there, right? Used to keep.
That's why it burned.
Yeah. Instead of looking at the whiteboard, he will prefer to.
Yeah.
You see the TV. Okay. Very good. You can turn it around, that would be easier.
No, you can see.
I don't have to see this.
You have to move it, turn it a bit more. Yes. That's good.
The homework 1. The caution that it's only 2 problems that is due, right? Keep repeating it, don't get overwhelmed, don't give up on the, because I would think that 28 problems can be very discouraging. So, it's due on Tuesday, so that's the next lecture. It's relatively far.
The homeworks are physically turned in, right?
Yeah, physically, I mean, everything is physical because it's a small number, I prefer it.
Okay.
It's easier for me to grade.
Okay.
And I never, oh yeah, and it is not necessarily due before the class. Like the quiz is due right before the class. Homework can be done anywhere before 4:30 and it is due in the physics office. Okay, physics office is 483 Neckers. It's actually not Neckers 483, it is across from it. 483A, I think, A or 483, across from it. That's a mail room. It has a photocopy machine and it's a mail room and there are this tiny pigeonholes for each faculty, but it's basically a letterbox.
And just find your name and.
And find my name and put it in that. That's convenient so that you can go all the way till 4:30.
Okay.
Physics office closes at 4:30, so that's a pricey pay, but I don't think I have had any problem. In the worst case, put it underneath my office or just try to be careful about it. But let's say 4:30 is the strict deadline. If at the moment I give you option of anything else, it's easy for you to go the whole night. So let's say 4:30 is the strict deadline. If you guys need extensions, typically I'm lenient as far as you all team up. Right? As far as you all say that, oh, the homework is hard, none of us has made any progress. And as a whole, I will do that. If it happens again and again, I will probably come and say that if it is not being productive for the whole class, then I might interfere. But I think most of the time it is okay. So if you're struggling, then convince others that others are also struggling.
We struggle as one.
Yeah, so that's.
And for the homework, you have to do all of them on 20.
No. No. Only two problems. Okay.
The first and second,
No, 10 and
10
28.
10 and 28.
Yeah.
Okay.
Read the first paragraph of the homework. Okay, I'm sorry. But I have pushed this a lot because otherwise all of you will drop out of this course. And no, 28 problems are not due, only two.
Okay.
I will not grade more than 2 hours. I won't even look at negative points for more than 2 problems. Get something like that. I encourage you guys to look into it because you should be aware of that. But my intention is not to make you guys work on the 28 problem. It's just that the recollection will sort of a review. You should be familiar with those problems. I think 3 of you have asked separately. So obviously, I didn't convey the point clearly. Okay. Okay. Any other questions on the homework? Okay, so let's.
Wait, and homework still on that same webpage too.
Correct. So there is a web page. You should be able to reach. I think I'll give it to you because. Yeah, we'll write it down. Because I haven't given the link on D2L, ideally I should put this on D2L also, but grad students seem to be knowing this site sufficient. So this is 2 zeros. Increase, that's a year, the first month of the semester, that's 01. And then it's SIU. And it's physics 520. Is that the way it is? I think so. It's not PHY, it's right? Yeah. Or go to the math methods website and just change this number. The last 4 numbers of the course and that you should
Okay.
Yeah, that's right.
get the right one. Yeah. That's the syllabus for you. So this means across from the office, but not the same. Okay. So we're doing electrodynamics here, so like if you've done mechanics of or motion that we described using Newton's law plays the central role there. Here, it is the electric field and magnetic field that plays the central role. Right, so the equations for that is the Maxwell equations, and let me write that down immediately. So, this is Maxwell equations. When did Maxwell write these equations? Anyone? Yes. 1800,
80 something.
Yeah, 1860. That is right before.
Relativity.
Tell that? Mumbling, it's like not understood.
Yeah. But for the industrial revolution,
Industrial revolution, what is the date you would put to that? Because steam engine is probably the industrial revolution, you would say?
Yeah, more.
So that's probably way before, yeah. So I would say. Yeah, I think the way I say it is that, I like to say. Is. Of course, Maxwell's equation has 4 pieces to that, right, that we will write down. And one of them is Faraday's induction. We are all familiar with Faraday's induction. Give an example of Faraday's induction. Give an example application of Faraday induction.
Like the Faraday's cage.
Not Faraday's cage. Faraday's cage is if you are inside an elevator, your cell phone doesn't work.
Oh, yeah.
That's Faraday's cage. You disconnect. If you want to kill, if you want to protect your country from any electromagnetic effects, you build a huge cage, metal cage around the country. But I'm saying Faraday's induction. Faraday induction. What is
change
that?
the electric field
If
to
you change
make-
a magnetic field, it creates an electric field. Or it creates voltage. Give an application of that,
Like a generator.
like a generator, dynamo, and
electric power.
hydroelectric power, exactly. So the main idea is that this was discovered only in 1820s. That you can change a magnetic field and create voltage out of it. So power that you see. All our powers at some point, somewhere, the magnetic field is changing. Or flux of the magnetic field is changing and it's creating a voltage somewhere. So it's mostly in dams where you have a turbine that is moving. But the point is, this was realized only in 1810, 1820s by Faraday himself. But that was such a big deal or such an important event. It's like a digital revolution now that we're going through. Once you have a computer, and more than a computer, once you have an internet, so many things that you can come up with that every other day you invent a new way. Or you can change this life, you can change your lifestyle basically. Our lifestyle has changed in the last 30 years. Same thing happened in 1820s. Every other day there were inventions coming up. You can build this device, you can build that device. And I wouldn't call, I think it's probably not the industrial revolution. Probably it contributed to that. Industrial revolution is usually associated probably with steam engine.
Kind of like towards the 1850s to 1900s.
Is that how it is?
Yeah, it's kind of-
After Renaissance.
Renaissance? Okay, I don't know the exact words. Quiz. Quiz. What is whatever this discussion is about. Summarize it in 3-4 sentences. Okay. I don't even know what the question is, but you guys.
Find the question and solution.
Yeah, so first discover the question and then answer it yourself. Reasonable? Okay. Okay, so Maxwell was in that region. It is 1860s. Between 56 and 60. 5 came in different pieces, but I think it is clearly at probably 1860 or 62, something like that. So what are the equations? He only, most of this was already existing. He only contributed to one piece, but the moment you put this all together, there was this big conclusion that there is a wave that could travel at the speed of light, which is the electromagnetic wave. That came only after Maxwell wrote down all this equation. So it was, he contributed to only one of them, but just the idea that he saw the whole thing come together, that was significant. And immediately within 10 years or probably 15 years, we had the telegraph come up and radio waves existed. So radio waves first time came in a laboratory, where from one corner of the room to the other corner of the room, you can press something and the signal could be detected there. But that was significant enough that within less than a decade, probably it went across the Atlantic. So it was very easy to implement and extend, I think. So what does Maxwell's equation denote? First one is Gauss's law. And what is Gauss's law? This is a review.
Yes, divergence of E is rho.
Is rho, yes, and you want to add something else?
Row.
Oh,
Rho or epsilon, very good, very good. So this is Gauss's law, divergence. So that leads us to the idea of this is the electric field, and this is the divergence of the electric field. So we are that's equal to rho. As a function of, yeah, what do you put it as R alone? It's R and T, right? It depends on R and T. Over epsilon naught. Electric field is the word there is field, right? In general, you're familiar with vectors. And now we are talking about a vector field. What's the difference between a vector and a vector field? But let's start with scalar. What's a scalar? Give an example of scalar. How about that? Example of scalar.
Speed.
Speed. That's a 10 mass. Scalar, yeah, it's a good point. Speed. Speed, I say, is not.
not.
I'm just being picky here.
The velocity would be,
Velocity is a vector, correct?
but speed.
The magnitude of velocity is the speed,
Yeah.
but scalar is. Yeah, sure. Speed is a scalar. I think surely it's satisfied as the conditions for a scalar. But, yeah.
Volume, I guess.
Volume is interesting. Yeah, volume is a scalar. Yes, volume is a scalar. What about area?
Area.
It has dimension.
It has a direction typically, and so area is area, at least area is associated to a vector typically, and the direction of it is perpendicular to the plane. So you have to talk about infinite area. So mass, temperature, speed is okay, I think. Yeah. So more broadly, a scalar is something that does not change under rotations. So I am having a coordinate system, let's say.
Travels in the same direction.
Tell that again.
Speed would be something that travels in the same direction. It doesn't-
No, just the magnitude of that, the direction information you have to remove, kind of. Is that probably that's what you mean? Like, you fix the direction and then that's the speed. But I say speed is actually a scalar because it doesn't change. I mean, the strict definition of a vector is that it remains the same after you rotate your frame. So what I mean is, so let's say there is a frame here. It says X, Y. Let's keep it two-dimensional, and this is a vector that could be your vector velocity, right? And now rotate it a little bit. That's your new frame. X prime, and that's your Y prime, and your vector has changed. In this new frame, the X component is different, Y component is different. In general, it's different, but what is same is the length. If I were to calculate the length of this vector, it doesn't care for the direction. So speed is the length of the vector, which remains the same under rotations. Under rotations, two things remain the same. One is the length of a vector. What else remains the same? I think there's one more piece, and here it's a relative angle. Suppose you had two vectors. This angle remains the same. If you have two vectors, then the dot product cosine theta, the theta part, that doesn't change. So that comes out important in other aspects when you're talking about scaling transformation, conformal symmetry, and others that plays an important role. But we won't be talking about it. But here I was saying, scalar, yes, speed is an example, mass, temperature. Here, velocity. Let's think of force. Force is a vector. What is a vector field? What's the distinction between a vector and a vector field? Lakshmi?
Collection of vectors.
Collection, yeah. At every point in space, you have a vector. So field is you have a land, and there's plants growing on it. At every point on that land, you have something associated to that point. So you associate a vector at every point in space, that becomes a field. Think of an electric field, that is a vector at every point in space. And in fact, this is more at every point in time also. So it's a vector field in that sense. So that's what we mean. So it's an infinite collection of vectors. And that collection is labeled by the position X. So that's a simple extension of that. Maxwell's equation deals with this electric field. And in Newton's laws, Newton's law again is mass times acceleration is equal to sum of forces, right? That's your Newton's law. And what is the purpose of Newton's law? Give me all the forces. So this is how it goes. Give me all the forces that is exerted on the mass m, and this equation will tell you the acceleration of the mass. If you know the acceleration, you can integrate, you get the velocity. Integrate it again, you get the position. So you can describe the motion of this mass m at any time t using this equation. What is to be given? This has to be given. Give me the forces, and the mass is given. Acceleration is determined by that equation. Right? That's Newton's law. Here, what are we talking about? What does Maxwell's equation tell? Or let's say Gauss's law. This is given. Give the charges, and Maxwell equation or Gauss's law or Coulomb's law will give you the electric field. This equation tells you what the electric field will be. If you give me 1 point charge, I'll tell you the equation for the electric field. Electric field is a collection of vectors at every point. At every point, you will tell what is the electric field due to the right-hand side, the charge density. Okay, so what is on the right side? Yeah, I should tell that first. So this is charge per unit volume at every point in space. This is also a field, but it is a scalar field. It is a scalar at every point in space. Give me what is the charge at here on this table, on this point, at every point, give me the charge. If you give me that to sufficient detail, this equation can tell you what the electric field is. Right? It's not a complete statement. We need a little more information. I will come to that in a minute. What is the charge density for a point charge? So let's say there is 1 point charge in space. What is its charge density?
Delta.
It's a delta function, so I will give you a charge Q. So it is charge per unit volume Q times, now we are saying it's only at one point, so that's a delta function, so that's. And I have to give you the position of charge. So like the Q, right? So this is a charge. Is delta functions familiar to all of you guys? Maths
Delta,
function?
yeah,
It's familiar, okay, very good.
yeah,
Dirac delta function, it's basically exists, there is a value at one point, zero everywhere. Very weird function, like probably doesn't satisfy lots of properties of a mathematical function, but it's very useful, extremely useful. As far as you stick to the rules, it can be very powerful, but be careful, it doesn't satisfy all the rules that a mathematical function has to satisfy. So if you blindly do it, you can make mistakes also. But with enough practice, that's what we are here for. We will see what are the pitfalls.
So actually, function is distribution.
Yes, if you think of it, if you want to make this more precise, you want to look at it as a distribution of functions. We won't do that, right? But good point. Quiz, in what sense, so the question is, in what sense is Dirac delta function a distribution of functions? So the question is, in what sense, what did Aryan mean when he said that delta is a Dirac delta function? Delta function, a distribution of functions. So very good point, but I feel we won't gain too much by going into that discussion, but it's worth realizing what Arjun pointed out. So let's make it a quiz, just read about it a little bit, even if you don't understand it.
so we have 2 questions now for the.
Yes, and it keeps building, right? So sometimes I don't think I've ever gone more than 5, but I have reached 5, I think. So they will tell you, but again, I'm not very picky, just write down the questions and answer a few of them and yeah, talk to them, they will tell you the secrets, so not losing. Find them very lenient, extremely lenient. Just write the questions down and submit. Ryan, you want to comment? Yeah.
Yeah, just kind of write down the answer to the question. Just, and that's it.
Yeah.
Alright,
Or just say that I cannot think of what to answer.
Or
Sometimes it is, I think it could be hard to answer certain questions, yeah. Okay, so this is charge. What's the unit of charge density? Well, units of charge density? Charge per unit volume, what are the units? Coulombs per cubic centimeter, what's the unit of Q? Coulomb, so what should be the dimension of a delta function?
Inverse of
Inverse.
Well, inverse of length, there are 3 of them in X, Y, Z, so delta function has a dimension of 1 over length, that's very useful.
Number volume.
There are 3 delta functions.
Oh, there's 3, oh.
Right, so what happens is that if, for example, let's say, I say a delta function of velocity, right? So there's one delta function, V minus V1, like V minus 3, let's say, right? In some units, 3 meters per second, something like that, right? What's the dimension of this delta function?
V is 1 over volume.
No, I meant V is 3 meters per second.
It's
The velocity. Just randomly coming up with. Never, I think you never talked about a delta function. Suppose it was, what's the dimension of the delta function?
it should be inverse of the argument. It's 1 over V.
Inverse of the argument, a very good point, right? So it is the inverse of whatever is the argument. Here it will be 1 over meters per second. Right, whatever this argument is inverted. Right, that's what the unit of delta function is here. What do I mean by delta Q? So that requires some explanation. There's a 3 written there. That means 3 delta functions. This is a vector. There is x here and an x cube, right? So this means delta of x minus x cube, delta of y minus y cube, and delta of z minus z cube. So where r now is x I hat plus y j hat plus z k hat and r cube x cube. So what that means is that if I were to have, if I represent this in 2 dimensions, so that's my x, that's my y, then x is equal to x cubed, right? So that's my x cubed here. And that's my y cubed. Somewhere there is this point. At this point here, only on that point in this whole plane is this function not 0. Everywhere else, this function is 0. That's the position of the charge. At that point, the charge is that, in fact, at that point, the value of this delta function is all the way to infinity. But those 0 and infinity come in such a way that when you add them all up, it gives you 1. And we'll talk about that more a little bit. Okay. Clear? That's here, and that's what this notation means. Epsilon naught, that's the permittivity of vacuum. What's the value of epsilon naught? Let's say in SI units.
8.85 times 10 to negative 16.
If I'm talking to minus short, right? So good, right? So Newton meter square. There is also mu naught, which is the permeability of vacuum. What is that equal to?
4 pi 10 to minus 7.
Minus 7. Yep. And what is that? So that's Tesla, I suppose. Tesla I amps divided by amps. Tesla meter by amps, I suppose. But not over 245. So. And what is this equal to? What's the product of that? That's fair.
One over C2.
So that's the big deal. That these two are constant. These are wherever you go in space and time, whichever galaxy you are, this value doesn't change. That's a universal constant to our understanding. And that means that speed of light is a universal constant. And until Maxwell's time, this was not realized, right? There was no such universal constant. And this is in direct contradiction with relative velocity, right? This leads to the idea that if you shine a flashlight and if you're moving with it, then what's the speed of the flashlight, right? Or the speed of the light that is coming out of that. And that led to the idea of relativity, or the contradiction between those ideas led to the idea of relativity. That's a product of these two constants. What about mu naught over epsilon naught? What is that?
Was it the chi?
No, chi. And if you call that chi, that's fine. But you mean the susceptibility?
Yes.
No, no. This is more familiar in engineering, especially if you're working in antennas and probably electrical engineering. That's it has to do with the resistance or impedance of vacuum. So. Give me the number, right? What would be the units of that by the way? I almost kind of gave it away. Impedance of vacuum, what would be the unit? Resistance of vacuum?
The ohms.
Ohms, right? So it will be ohms. And then the question is, what is this value? Find the value. Quiz, yes. Sorry. I think it's a review session, but it's easy to ask questions and. Okay. Quiz, yeah. Okay. Like, because it's usually not talked about, like this is more popular, but this is well known. So it's kind of nice. Okay, so that's all our Gauss's law. And what's the meaning of a divergence of a field? Well, how do you, if you have to explain divergence of a vector field, an electric field to someone, let's say an undergraduate student, how would you explain that?
Depends on the source. If you have a source, it was outward or inward point.
So here is what I got. So let's say there is a point charge. And there are 2 point charges. Q1 and Q2. Is that clear enough? And there is an electric field associated with that. I want you guys to imagine that. Right? All of us should be able to imagine what's the electric field due to 2 charges. Right? If not for either of them, they are radially outward. If there are 2 of them, they cannot interfere, so they push on each other. And let me try. Yeah, let me try. So, this will look like this. Is that familiar? Right. Okay. Now, telling. So that's the electric field due to 2 charges. All of us good with it? That's the electric field. If I take the divergence of the electric field at this point, so this is a special point, let's say, I'm interested in that point. I want to keep a device there. And I'm interested in knowing what is the divergence of the electric field at this point. What is that equal to?
It's 0.
It's 0. Very good. That's very good. And why did Matt say that? What motivated? How did he deduce that?
I had a reason, but it
Because whatever comes into that region, it goes out.
No, Matt says that divergence at this point, this special point, I didn't even clarify which point that is, how far it is from. But he says it is 0 here. Is he correct?
Yeah, these are point charges, right?
Yes, these are point charges.
There are no charges here.
There's no charge. Your right hand side is 0. Left hand side has to be 0. Mathematical statement, mathematically equality. Right. Right hand side is 0 because of delta function property, right? The charges exist only at 2 points. Right. So the divergence of an electric field is equal to 0 if there is no charge sitting there. Unless you're sitting on top of a charge, you're superimposing yourself with a charge, divergence of an electric field is 0 right away. A very easy statement. But that doesn't help with the interpretation, right? My point was what do we mean by divergence of an electric field. For that, let's go back to the gradient of an electric field. What's the difference between gradient and divergence?
Gradient is a scale.
Or it operates on a scale.
Operates.
Yeah, after that it gives you a vector, right? It gives you a vector, but it operates on a vector, and divergence is a scalar product of a vector field. It operates on a vector. So my train of thought here. Are all of us familiar with gradient and divergence, and are we comfortable a little bit with it? Or let's say, are we aware of gradient and divergence? Right, all of us aware of, I mean, fluency probably comes, takes a long time to. But at least you have worked on problems related to that. Let's have a gradient in picture for a few minutes, right? Gradient is always acting on a scalar field, that's a scalar field. Is that okay? I think, qualitatively speaking, what that means is clear. How will you go about calculating this? Like, suppose I tell you that. What's an example of a scalar field? Simplest example.
Temperature.
Any? Huh?
Temperature.
Temperature, but give me an actual function. Random arbitrary function.
X squared y.
X square y. So let's say phi is equal to. Let's make it simpler a little. X square y is also good enough. So let's say this is phi. Right? What is the gradient? I don't want you guys to calculate this by doing the algebra. That's surely one way of doing that. But I want you to tell me what's going to be the gradient. This is going to be a vector field, right? So this will be a vector field. Let me call it V field. Right? Why call it there? Let's call it E. Right? Electric field is potential of that. I think this minus also. Now I want you guys to tell me without doing the algebra. What is this going to be equal to? 6. Huh? X. Oh, you're doing the algebra in your head. Correct. Okay, yeah, good. Okay, so I'll give you up. Okay. So this is minus I hat. So you this d by dx of this. So it is 2 times x minus j hat 2 times y and minus k hat 2 times z hat. Z, right? That's what you're suggesting, I suppose, right? Good. But I meant, so that's still, it's an algebraic statement. How does it look like? Like, how can you get this qualitatively? So notice, if I were to write this as minus, this is minus 2, let's say, this is x I hat plus y j hat plus z k hat. What is that?
Or
R, right? Very good, right? So very good. So that's minus 2 vector R. Right? That's geometrical. So that's a visual field for this. This is algebraic, right? Now, how do you get this? How, if you want to get the gradient from a function, how you go about this is a field, that's a scalar field. Make it a constant. Like fix a constant. So phi is constant, right? Think of, let's say, 3 square. If x square plus y square plus z square is a constant, I just picked 3 square. What does that represent? That represents a sphere. Right? So it's a surface of constant phi. In this case, it's wherever it is 9. Correct? And it turns out to be a sphere. I picked it so that it's easy to visualize. So that's a surface of constant phi. In this case, 9, right? And its gradient comes out to be minus 2 r hat. And if you notice, that's the center, that's radially outward, correct? That's radially outward. It will always be perpendicular to the surface of constant phi. Find the surface where it is a constant at every point. Draw the normal to that surface, that's a gradient. Okay. Like for example, in this room, that is temperature at every point, that's a scalar function. And look for all the points in this room where the temperature is exactly 23 degrees Celsius. Okay, that's 46 plus, so that's about how much? 80 degrees, 75, 76 degree Fahrenheit, I guess. So every point in this room that is exactly 23, it will come out to be a surface always. Okay, and sometimes it is a closed surface. Is that clear what I'm saying? If I fix my value of the function, it leads to a surface in the volume that we are talking about. Once you have the surface perpendicular to that surface at every point in space, wherever that surface is, that's the gradient. Okay, so it's always a normal to the surface of fixed phi. I can have a lot of surfaces, like if you have a room, so this could be the surfaces, right? So this could be your surfaces. And it's two-dimensional, of course, and the gradient will be always perpendicular to that. But at this point, this is that clear? So that's a physical interpretation of a gradient. Divergence is whether that, so that's a gradient operator. Next is divergence, and then comes a curve. Divergence is always whichever field you're talking about, there is a source to that. Source to that field. What's the source of an electric field? It is the charges. They have to originate from a positive charge and they have to end in a negative charge or at infinity. That's only two options. Right? Electric field lines have this property that they either end at negative charge or at infinity. They have to satisfy that. And the divergence of the electric field is pretty much telling how much of a source or sink is that at that point. It's equal to the source or sink of the electric field. Source or sink of E. But you want to visualize that better. It is how much you're radially coming outward. So remember, source always has this feature, right? So that's a source. Basically, electric field cross at that point. Right? It's not really crossing, it's originating from that point. Right? It's a measure of how much of that point is a source of an electric field. Are they originating from it or not? Right? That's a if it's divergence-free electric field, that means there are no sources or sinks for that electric field. So that's the point. And usually you say, for example, if you have a positive charge, so this is having a divergence. It's at some point in space, that is a divergence, there's a source out there. So that's what we mean by divergence. That's similarly, we can talk about curl of an electric field. That's curl, all of us are familiar with this. And what is the curl of an electric field equal to?
Change of magnetic field.
Oh, yeah. See, that's correct.
What was there?
Change of magnetic field.
Change of magnetic field. I didn't hear. Yeah, that's okay. Over time, yeah, change in magnetic field over time. That's correct. Why are you confused?
Yes, no, like there's a zero for a curl, right? Maybe curl of a magnetic field, right? Curl of B is zero, right?
It did not be on. Are you talking about monotone? Can it not be? No, so it's.
This is equal to del B over del D. That's what is this law equal to? You have a good point that I think what you're talking about is electrostatic. In electrostatics, the curl of the electric field is zero. That means the electric field cannot go in circles. Electric field necessarily has to start from a positive charge and has to go in a negative charge. Magnetic field, notice, where does it originate from?
Dipole.
It is always rotational. Dipole. Yes, good point. Dipole, but it's a positive and a negative charge. In that sense, it's not that, but good point. Yeah, it's always a dipole that is the origin of a magnetic field. But in a Faraday effect, you will see magnetic field in a circle, like you have a current carrying wire. And magnetic fields are always circle, so it never ends, right? It's a circular, and that's the curve. So if electric field is not equal to zero, that means that you can have electric field lines going in circles. Is that possible? Electric field lines not originating in a positive charge and ending in a negative charge, is that possible?
Or, I mean, exception.
That's, I think we never see it, so the point is, yeah, you say no, because most of the time we are doing electrostatics, all of the first semester of this course, we did electrostatics. In electrostatics, this is zero. Right, and in that case, electric field cannot originate from randomly in space. But if it is not zero in Faraday effect, for example, Faraday induction that we talked about, that electric field can go in circles, right? And we will talk about that. So electric field, if you're not in statics, most of the times we are in statics, but if you're doing radiation on other mechanisms, you're not in statics, you're in dynamics, and then that's not the case. Okay. So if the curl is not zero, then you can't go in circles. The field can be in circles. Okay, so all this starting from here, but I kind of touched on various things. That's your divergence of an electric field. The second is let's say the curl of an electric field. What is that called? Faraday's law. Let me not. First, let me do that. What is the divergence of a magnetic field? Equal to, this is charge density. What is the source of the magnetic field?
Zero.
Zero. There are no north poles and no south poles. There are no magnetic monopoles. So that's equal to zero. What the name for this equation? Apparently, any name for this equation you come across? Let's leave that open. The third one is curl of electric field, which is Faraday induction. That's a Faraday's law, which is del cross E. Again, function of R and T, that's equal to minus time derivative of the magnetic field, the same equation that I was trying to write.
Is number two Gauss's law for magnetic?
Correct, that's the best you can do, but Gauss's law, we take away for that, but typically there is no specific name given to that, but the best is to do Gauss's law for magnetic field.
Is he looking for magnetic monopole?
Was I looking for?
No, are they still looking for it?
Yes, okay, so the point is, good point, okay. Now magnetic monopoles, as all of us here know, probably is that if you take a magnet, break it into two, there's a north and a south pole. Break it again into two, they will again always have north and south pole. Till now, we have not been able to separate a north pole from a south pole. That's an experimental limitation. And you might always say that there is some exotic particle in some galaxy which has a magnetic monopole. It's just that around us, we have never seen it. Like many of the elements in a periodic table, we don't always see it around us, right? So it's always a possibility that it. So that's a very simplistic argument. But the more of a reason why you would like a magnetic monopole to be there is that there is this theoretical prediction, and that is by Dirac. He said, or he showed that if a magnetic monopole exists, if it's true that this is not, the right hand side is not zero, instead you say that there is a magnetic monopole density. If that was true as a theoretical statement, let's assume that that's the case, then we can go through certain steps and use quantum mechanics. Okay, quantum mechanics plus the fact that magnetic monopoles exist implies that the electric charge of any particle times the magnetic charge. So this is electric charge on a particle, for example, on a proton. The electric charge is 1.6 into 10 raised to minus 19 coulomb, right? This is the magnetic charge, which we never talk about, right? This is not existing. The magnetic monopole that we talk about. This times this has to be equal to h bar times n, where n is a number. The n is equal to 0, 1, 2, and so on. Which means that if G is put in the denominator, it explains why the charges are discrete. We always find charges in discrete elements of the electric charge. Why? We don't have a reason. It's just an experimental fact. But if magnetic monopoles exist, that explains that. That clarifies why it is, right? So due to that reason, there is a theoretical bent or bias toward this must be true. Like there is such a nice prediction associated with magnetic monopoles, it must be there. So there is a huge bias among theoreticians because there is a strong, very neat prediction that charge is quantized in that case. But all searches as of today have failed to find a magnetic monopole. We have put bounds on it. After you make a search, if you don't find a magnetic pole, you say that, oh, it is not there within this limit. So if you have the units of magnetic monopole within certain limit, they have not found it. But that doesn't mean that it doesn't exist, right? So it is never, you can keep expanding your range and you can never stop it unless you come up with another theoretical argument saying that no, this doesn't exist because of certain reason, theoretical contradiction in a sense. So did I answer that question? So there's such a nice prediction associated with magnetic monopole that one begs for it must be there.
So I've heard there was an early universe.
Yes, the best, again, those are theoretical, right? I mean, you always say that, oh, if you want a standard model that is all the particles which have magnetic monopoles, they're associated to be Hooft. Yes, that's correct. But all those are theoretical. We haven't experimentally verified none of them. So in the current literature, magnetic monopoles don't exist, right? Since it's not there in experiments, we don't have, but yeah, theoretical, in theories, it is conveniently used. But it has non-trivialities also. But good. Okay, the fourth one is, what the fourth equation is it called? Or the name of the fourth equation, fourth Maxwell's equation? Ampere's law. Okay. Here's law, and that's equal to del cross. How do I write this? B over naught. It's equal to time derivative of epsilon naught times x electric field. And this epsilon and mu naught are all there for a reason. And plus current density. This is current density. Okay. Now, this equation, who was the first person to discover it, let's say? Gauss's law? No, it was not Gauss. He stole it. It's not. Coulomb, right? This is Coulomb's law. Coulomb's law is written as Gauss's law in the differential sense, but it's Coulomb, right? So this is Coulomb. I think a few decades before 1800. So this is Coulomb. Right. And this was never a law. I think it's only recently, this has been realized the importance after Maxwell's equation this became important. So ignore that. This is associated to Faraday in 1820s, right? This is associated to Ampere, right? So what did Maxwell do? Now, why is Maxwell's equation named that? What did Maxwell do here?
He categorized it.
No, he did more than that.
And the first term, I think, is for
Very good.
Maxwell.
Yeah, so what Ampere wrote was not this. Ampere did not have this piece. Like if you remember your Ampere's law from your introductory physics, it says del cross P is equal to J, the current loop integral of the magnetic field is a current. That's not having this. It was he who came up with the argument that, and just on a thought experiment, it's very remarkable that he just based on thought experiments, he argued that this must be there. And that immediately led to wave equation, because you can talk about a wave equation. We will talk about that soon. And that led to the idea that there is field of light. But let's talk about this argument Maxwell had in a few minutes.
That why some people call it Ampere Maxwell's law.
I don't know if that is called, but that's reasonable to call that. But typically, I think most of the standard textbooks I've seen, they just call it Maxwell, Ampere's law. But it's reasonable. I wouldn't be surprised if people do credit it to him. But instead, what they do is they credit the whole set to be, because that really brings it all together. So that puts the constraint correctly. Otherwise, remember, these are all constraints, like electric field. Think of any possible field of vectors, and this puts a constraint on that field. It's like saying that out of all possible functions, you're picking that only those functions that satisfy this are allowed. So these equations put strict constraints of the electric and magnetic field. Not only that, it puts a unique constraint. Once you give me the rho and J, the electric and magnetic field is unique. Without this piece, that uniqueness is not there. So it's more than just collecting those equations. It just made sense to then invert the equation and talk about electric and magnetic field. But let's very quickly, since we're talking about Maxwell's equation, we should know what Maxwell contributed. This is one of the arguments. I'm sure people have read various ways he argued this. This is what's the difference between this and this? Symbolically speaking, that's it.
It's a sad
That's a capacitor, correct? So let me enlarge this capacitor. Right, so I'm going to make this capacitor really big, just for illustration purposes. That's really how a capacitor is. It needs two parallel plates, right? These are physical plates there. And now, if this is a positive charge, and if these are all conductors, the charges are free to move, and they will stay away from all the positive charges here. So you suddenly get all this positive charges here, correct? And oh, sorry, what did I do wrong?
Why is it
Negative.
negative ones?
Sorry. It's not thinking. And that's your electric positive and negative charges. Immediately you know that this creates an electric field. Right. And yeah, so that's the picture we have now. And what is Ampere's law? Remember that this is Ampere's law is this: del cross B is equal to J. Right. Oh. I'll take 2 minutes. Okay. Comments are stop and del cross B is equal to G J means that loop integral of B dot dl is equal to current. In fact, it's mu naught I. Because there is may not. A loop integral of that. That means that if I make an Amperian loop here. Right, is that clear? And calculate, there is a current going through that. There's a current going, I'm just switching it on. After a while, it just stops, right? But the moment I switch it on, there's a charge that moves from here. There's a current there. It changes with time. And that tells me that there is a magnetic field around it. So around a current, there is a magnetic field, no surprise in that. But this is having an area associated with it. Right? Remember, loop is the important point. We're saying that there is a loop and there is an area associated with that. But why should I say the loop? So Maxwell's argument was that once you have that circumference fixed, why should the area, so if you have this to be the loop, this is the area enclosed by the loop, but that's not unique. This is also an area enclosed by the loop. Like think of a dome. Like that's also an area enclosed by the loop or area bounded by the loop. So he said that I won't use the law like this. Instead, I will have my bound going through this. So the area is going through in between the two plates. There is no current there. So the left-hand side or the right-hand side is zero. So the magnetic field should be zero, right? But is that that's a contradiction. One area gives me that, the other area doesn't give you that. That's the idea of Stokes' law, basically. So he argued that there must be here also you want to contribute. It is an electric field that contributes you. So you want that both to not have any contradiction. So when you be taking it through this, it's an electric field that's contributed. When it is taking it through that, it is J that is contributed in such a way that it's unique. I mean, it doesn't matter which way it should not depend on your choice of the surface. Right? Even though the bounding element is the same, the surface is not unique, it should not matter. Right? Few lines on this, the quiz. Okay, whatever I discussed here. How did Maxwell come up with the modification of Ampere's law? Is that clear? How did Maxwell come up? It's there everywhere on the internet, but try to understand it. It's kind of a neat idea, very neat idea. Okay. It involves Stokes' law, Stokes' theorem in the strict sense. Okay. And I'll stop.
Wait, how did Maxwell?
How did Maxwell modify Ampere's
Ampere's law.
law? Right? Using Stokes' theorem. That's a hint. Like Stokes had just got his Stokes theorem in fluid dynamics about 10 years back, like in 1950s. He contributed significantly to fluid dynamics. And so it was very easy, or Maxwell, I think, got motivated from that. Relation. Okay. So does this ring, is this reasonable? Is this?
It's been a while since I've taken physics, but
Yeah.
it's coming back.
Okay. But it's not driving you to drop off the class.
Yeah, so
That's okay. But not 28 questions, only 2 questions. Okay.
Should I end the meeting?
Yes, end the meeting.